as we go with that as well. So the notebook should be in the Slack channel. We're going to use the Google Colab notebook. So let me know if anyone has trouble accessing it while I pull it up. Okay, so is everyone able to access this forecasting with Kronos notebook? While you're pulling it up, I'll start walking through it. At this link on forecasting with Kronos, I provide a link to AutoGluon quick start on how to just handle time series in AutoGluon in general. But we will walk through that in this notebook also. But if you're interested in more details of how to use some of the general time series models that we looked at earlier, such as the local statistical or deep AR, walking through some of those other tutorials may be interesting. So we provided the link. You can also make your own copy of it. So if you click on Save a Copy in Drive, you can have your own copy of the notebook to edit as well. So today we're going to look at how we can call Kronos from AutoGluon time series. So it includes the whole family of Kronos forecasting models. We can go from the tiny size to the large size and also the faster Kronos Bolt models. We saw that they're pre-trained on a large collection of real synthetic time series data and it can be used out of the box. So the main data structure we're going to use is this time series predictor API. It's going to basically import our CSV file in a data frame structure. We'll first look at the zero-shot use case of Kronos, comparing Kronos base to Kronos Bolt, and then perform fine-tuning. And look at how we can also feed in covariates in the structure also. So the first step is we're going to pip install AutoGluon here, which could take a couple minutes. So let me know if anyone has questions with this installation. Okay, so while that's running, as I mentioned, we're going to be using this 3-line of code structure of the .fit and the .predict models, which is how AutoGluon is based. But Kronos is going to be different than classical models in AutoGluon TS because we don't need to do the training. We will perform some fine tuning, but out of the box, it's already been pre-trained. So what does the .fit method really do? We don't need to actually call .fit on the time series data. When predict is called, that's when it's going to be doing the expensive inference computation. And it scales linearly with the number of time series in the data sets. So in this aspect, it can behave similar to ETS or ARIMA, where all the computation is happening during inference. There's no training on the model directly. So we can call, as I mentioned, the original Kronos using the T5 large. If you click on these links, it will take you directly to Hugging Face, where you can also just directly download the weights and run them outside of AutoGluon, also using the GitHub repo. So if you go to Hugging Face, you can choose which Kronos model you'd like to use. So they range from 8 million to 710 million parameters. And they're already available for us in AutoGluon. So all we need to do is set which pretext we want to use. And then we also have the Kronos Bolt. So for Kronos Bolt, we'll be looking at using the small model, and for Kronos, we'll be using the tiny model. Here are the presets. So, and the original Kronos presets. So these are the ways that we can switch between the different pre-trained weights to call. So here we can run this tiny Kronos on CPU, but recommended for any of the larger model sizes to run on a GPU. Kronos Bolt can be run on CPU and GPU though. If you want to explore outside the tutorial other ensembling of Kronos with other time series models in AutoGluon TS, AutoGluon has these other presets such as medium quality or high quality and best quality. And these are some of what they call the best quality predictions. And there may be a trade-off with the best quality versus time, and that will be in this .fit documentation. But first, let's get started at looking at the zero-shot forecasting. So we'll be looking at a subset of this Australian electricity demand data set to see Kronos and Kronos Bolt in action. So step one would be, we're going to load this time series data frame here. and our time series predictor. And let's give the path to our CSV file. So this is where you'll load in any data set that you like. So here we can use, and what does it look like? So in the simplest case that we have no covariates, all we're going to have is the item ID. Here in this data set, we only have one time series, so one item ID, and this corresponding timestamp. So we'll see that the frequency of this data set, which is going to be stored in the data set meta information, is in 30-minute frequencies intervals. We're recording the target value. Now, let's say that we'll see an example of this later, but we also have target related time series. So let's say we have covariates, they would be additional columns. That's how you can feed them in your data sets. It will subtly differ if they are related time series that are only known in the past versus the present. So for here, I'll stop and walk around if anyone has any questions loading the data. Yeah, if you have a question, feel free, raise your hand and I can walk over and help. Okay, so we'll see that this data structure, you can call data.head on it. It looks like, if you're familiar with pandas, like a simple pandas data frame. And now we're going to define the problem. So we're going to say we want to predict prediction length equal to 48. So we're going to be predicting 48 values in the future. First thing we need to do is do our train test split. So in time series, this is different also than in machine learning, where typically, simple case, let's say we have tabular data, we're going to be taking 80% of the rows, maybe for train, and 20% for test. In time series, it's different, where we're actually going to be chopping in the time dimension. Under the hood, this does a type of back testing. So what do I mean by that is you can have the same time series in your train and test data set, but you cannot allow leakage in time. So we're going to chop it at time t, and the test data set will be the full time series. So this is going to be partitioning our time series here. And the usage, again, is similar to the scikit-learn functions. So now let's select Chronos Tiny. So we'll first start with the base Chronos model that I mentioned was slower, and it does the simple binning, feeding in the time series one at a time, and also value-wise. So we're going to call .fit. We're going to feed in the training data to this, and also whichever model we'd like to choose. Okay, so it's saying it's beginning the training, but technically for Chronos, there's no training going on at this step. So if we parse through some of this output, we see that we're going to be using the weighted quantile loss as our evaluation metric. You can also override to whichever evaluation metric that you like. And these are the hyperparameters. So hyperparameters we'll see later is what we can override, for example, to do fine tuning and also pass in the covariates as I had in this example in the slides. If you want more complicated backtesting, so you can set this parameter. So this is looking at the number of validation windows. We're saying we're just going to evaluate it at one time slice. You can also do rolling or sliced evaluations. This is our prediction length. We're going to do the full weighted quantile loss. So we're going to evaluate it averaged over all the quantile intervals. You can also set the random seed. And it is able to infer the time series frequency correctly as 30 minutes. And this will just give us some stats of the time series. So we see it has 172,000 rows. We have 5 time series, and the median time series length is here. We only have a target column, so we do not have any additional features in this example. So what AutoGluon does in general is it's going to do a ranking of the models subject to whichever evaluation metric that you select. So it's going to rank them according to the weighted quantile loss. This is a bit of a confusing convention, but since it's ranking based, sometimes if it's a metric where lower is better, it's going to have the negative sign of the metric to be able to rank them from best to worst accuracy. So if that step ran for everyone, we should see that the Kronos did not take any time to fit. So the fit call is just calling a proxy for the time series predictor to do some of its chores under the hood, such as inferring the time series frequency, as we saw, and saving the predictor state to the disk. So now let's actually call the predict method, and then we can plot the time series to visualize them. So the way that we call predict is just predictor.predict of our training data. And then this next line here is going to be plotting the time series. So we're going to be plotting the first two items in the data set. And then we're going to be looking at the last 200 points. So these are going to be shown in blue. Our forecast is going to be in orange, as well as the confidence intervals. So now let's run this line. So here's what will take some time, since we're running the original Kronos model with 8 million parameters. Any questions on this so far? Oh, sure. Oh, you mean where it infers the time series frequency of 30 minutes? Yeah, I think that's just using some basic statistical methods, kind of like even subtracting the timestamp and making sure if they're at regular intervals, you can get an estimate of the frequency. So yeah, that's not doing anything fancy there. So hopefully, if it ran for everyone, we can see, okay, the time series here, it doesn't look that accurate. The small base Kronos model, right? We see, okay, it's able to kind of copy this past time series, but it's not able to get this dip. So the seasonality is correct, but maybe the magnitude isn't. Also, the forecast isn't fully contained in the confidence interval, which is shown in the light gray, in the lighter orange color. Next, we're going to look at using Kronos Bolt. So can we get a better prediction with Kronos Bolt? Here we'll look at the small model. So it's not a fair apples to apples comparison because Kronos Tiny to run on our laptop or CPU in this example only has 8 million parameters. This model is going to have 48 million parameters. So it has 6 times the number of parameters, but we'll see it actually runs faster as well. We can easily switch using the same code, just changing this preset option from Kronos to Kronos Bolt. So here I'm going to specify I want to try Bolt Small. If later anyone wants to try the larger models, that's easy. You can just try Bolt Large here or Bolt Base. But for now, we'll try the small model. Again, we're going to initialize the time series predictor with it takes the prediction length as its input. We're going to call .fit here on our training data. And this will be similar to what we saw with Kronos. The only difference now is our model path, which is specifying which path to get the weights from Hugging Face is pointing to Bolt Small. And we see that it still has the time series frequency of 30 minutes. Okay, so now we can do the same thing. We can call .predict and then plot the corresponding time series. In this case, visually, Kronos Bolt also looks better than what we saw with the Kronos Tiny model. Here, in particular, you can see that the forecast is contained within the confidence intervals, and it is predicting kind of this magnitude drop better than the smaller Kronos model did. Question? Oh, so it will default to GPU if GPU is available in the code itself, yeah. And then you can try running some of the larger models. You could also potentially do that. Yes, so if anyone... Yeah, that's what I wanted to point out too. If anyone wants to use NERSC after, you can definitely feel free to try to larger models on GPUs as well. Like yeah, that's a good question. So what is making Chronos Bolt be able to predict this dip, whereas the other Chronos we saw was not as accurate? Yeah, I don't have an exact cause, but that would be interesting to look at. It's potentially due to, we have multiple changes, right? We're doing the patching, we're using a different loss function. So potentially using the quantile loss is actually beneficial here to learn this as well. And another thing could be it's also a larger model size. So it has advantages, this model, of being larger, and also it's taking more of the context. So Chronos Bolt actually takes up to 2000, so further back than what we're seeing here of the history. So potentially, if this happened before in the history, it's able to see that better than the Chronos model, which only is taking in 500 of the history. Question? Mhm. Yeah, so that's already done for you in the pre-training. Yeah. So technically that's not happening in the fit function, but that's going to be happening in the stop predict function. So it will first normalize the data and then feed it through the forward pass of the model. Right. Yeah. Then it will map it back at the end. Exactly. Exactly. Yeah. So for each time step of Chronos, since it's autoregressive, we're calculating the sample paths. So we're calculating maybe 100 samples to get these estimates. So that's what Chronos is doing, but Chronos Bolt is directly outputting the quantile forecast. So that's another difference between them, which is analogous to the difference between DeepAR and MPCNN also. Mhm. Yeah, that's a great question. And one that we typically get. So yes, it would be different every time. So we do the training on fixed random seeds to at least make sure that you can have a reproducible result. And you can also pass the seed at inference time. That's another parameter that you'll see here in the notebook. But yeah, if you do, let's say, want the uncertainty, you could run it multiple times and measure that as well. So in the paper, we report basically the variance over multiple seeds. Yeah, good question. Because a lot of times in practical use, we get this question all the time. Most customers want it to be deterministic. So in that case, yeah, it doesn't fully make sense in that case, but we pass the seed as a sanity check. Question? I see what you're saying. So you mean the different time series at inference time or even in the pre-training? Yeah, so the variance can handle very drastically, actually. So if we go back to one of the past slides with that shock example, let's say we had a discontinuity. In that case, the variance is very heteroscedastic. We see it's very small and then can be very large. So it definitely depends on the particular time series. If you have more homoscedastic data like this, that's kind of has a nice period, you'll see it be more uniform and maybe largest at the peaks, for instance. So yeah, the variance does depend on the particular time series and how hard it is to predict or not. And that's kind of the idea in the constraint works is, can we use this variance to tell us kind of exactly where we should impose constraints? Oh, the source of uncertainty in this model or in general? How does it determine? Yeah, so like if we're thinking about the base Chronos model, right, it is calculating through the cross entropy loss the probability of each token being the exact. So we get kind of the probability distribution straight out by using the softmax function in that case. So that's a nice way. In some of the other deep learning models, like for example, DeepAR, we are assuming a Gaussian distribution. So there are different ways to encode the uncertainty. In the quantile version, we're directly trying to estimate the quantile forecast. So there's pros and cons to either having to assume a distribution. We have other works related to DeepAR with SQF, which is using splines and the CRPS loss function. So you can kind of get the uncertainty without having to assume, let's say, a Gaussian or a simpler distribution. But yeah, that's a great question. Oh, I see. So kind of you're talking about if the model gives a feature importance or yeah. So I think we can get that through AutoGluon. So typically if you're running like the tabular models, they will rank them in feature importance so we can get those scores. For time series, since we don't have the covariate support in Kronos exactly, I'm not sure in the Kronos model if it will do the ranking, but definitely for the other models, we do a type of ranking of the features. Yeah, so the response curve we don't have in AutoGluon TS, but we have that in some production systems, kind of like a what if analysis. That would be a great way to try to use it, and kind of some of the motivation exactly for the probabilistic forecasting too is in what if scenarios and scenarios like that. Okay, so remember these examples were zero shot, so it hasn't seen this time series before in the pre-training data. So let's say if we're not happy with the result, we can try fine tuning, or you can try also this fine tuning code on your own custom time series after this as well, or trying to reproduce it also. So AutoGluon makes it easy to fine tune the Kronos models. And all we need to do is we're still going to create our time series predictor with the prediction length. Probably could have saved this call. We're going to call the .fit method, feed in our training data again, and now we're going to modify the hyperparameters. So we're going to specify these are the hyperparameters for Kronos. We're going to specify the model path to the weights. And here we're going to run two variants of Kronos. So this is how AutoGluon is going to rank, is zero shot or fine tune Kronos better on this data set. So first we're going to say, okay, let's run the zero shot that we already ran. And now let's compare it to the fine tuned version. So we're going to specify we want fine tuning to true here. And this is just the naming of how we want it to enable it. So we will name it the fine tune Kronos. But to run the fine tuning, all you actually need is this line here. And we can set a time limit as well. So here the time limit is set to 60 seconds. You can increase that also so that it can fine tune for longer. Enable ensemble I have to false, but for higher accuracy, you can even turn on ensembling. So this can ensemble potentially both of these Kronos models together or ensemble with other time series models that you are listing here for it to consider. So now let's try to run this cell to run the fine tuning. Which will take a little bit longer to run. And notice I'm fine tuning on the Bolt small version. Yeah. So now it will be fine tuning on your specific training data. So the CSV file that we provided. So this would be the line to change if you want to input your own data here. Add a comment. It actually has multiple time series. So this data set has 5 in it. If you go back up here, it's just showing because we're only looking at like the first 5 rows, 1 ID, but there actually are 5 in the data set. I think I misspoke and said there was 1. If you look at the statistics, it mentions 5 and we plot the first 2. So it's still a small data set, but there is more than 1 in it. Yeah, I think here's the stats. So it's this many rows and 5 times series. And that's how you distinguish the different time series is through the item ID, right? So here we're going to have all the rows for the first item, and then the item ID will change, and you'll input the time series for the next. So it uses a standard CSV format. We had more complicated time series JSON data formats in Gluon TS actually, but the CSV is probably the most user-friendly. You see here. Okay, let's see if the fine tuning finished. Did anyone have trouble running the fine tuning? So this is saying that you can also change more control in the fine tuning. So all we did was set it to true, but let's say you want to play around with tuning the fine tuning learning rate. You can set that also through the hyperparameters here, and also explicitly specify the number of steps you want to run rather than setting a time limit. So this would be setting the fine tuning steps to 1,000 and changing the learning rate. For more list of advanced fine tuning options, you can see this forecasting model zoo link here also. So now that we've compared, and generally you can have a larger leaderboard than this, right? We can compare to all the time series data models that we saw in the talk also. But this is just an example of the AutoGluon leaderboard. So let's see, is it as expected? Would the fine tuning result beat the zero shot? And here's what you see here. It should be showing both the zero shot and the fine tuning. So I'm not sure what happened. Try rerunning the fine tuning, but what we should see is that they're both ranked with the fine tuning having better performance than the Bolt Small. What happened to you? It shows that for you? Okay. I don't know what happened at my end with rerunning it. Yesterday, it also worked for me. So what you should get is similar to what we have. So we have these tutorials on the AutoGluon as well. You should see something like this. So the Bolt fine-tuned has better performance than the zero shot. And this is the score test. You can specify again, like which metrics it's using. We're using weighted quantile loss. It will also take the time it took to fit as well. Any questions on that? Mm-hmm. Yes, so this is fine-tuning the entire model. So basically, it's using the same architecture as the pre-trained, and it's doing one forward pass-through. So it is doing all the data normalization for you as well, kind of under the hood, so you don't have to really worry about doing the data pre-processing yourself. You can kind of feed in the raw time series data too. But yeah, that's another question I got earlier, is if we can only fine-tune maybe parts of the model. That's not something that this current implementation is doing, but could be interesting also. Yeah, so that's a good question. So it will, if we're talking about number of time series, it's going to fine tune on all of them in your data set. And then it will fine tune, you can specify the specific context length of how far back you want to go in the history, if that's your question. So by default, the model is doing a context length of maximum of 2,000 historical steps. But that can be, context length is another, just in general, time series parameter that's important to tune of how far back you want to go in the history. That's something interesting we saw in the COVID forecasting too, actually, was that shorter context lengths on those data sets performed better, just because the data was so rapidly changing at that point that even having more of the history wasn't actually helpful. But now it might have changed, that it has a lot more historical data. Okay. Well, I'm not sure what happened on mine running it live here, but hopefully everyone else will see both of those listed. So that's how you can do the fine tuning, and I encourage everyone, if you're interested, to play around with it after on your own data sets. Feel free to email me with questions even after the tutorial as well. In the next section, we're going to talk about incorporating covariates. So we've all been talking about how can we use features outside of just the target time series. We'll see a data set which is representing the grocery sales of what this would look like. So Chronos currently is a univariate model. We talked about potential multivariate extensions that are currently under research, but right now it's univariate. So it relies solely on the historical data of the target time series for making prediction. But we know from real world forecasting systems that adding the related time series can help the prediction. So we can have holidays and promotions. So the idea is, what can we incorporate from the domain knowledge side to improve the language model more? Our original question was, can we just use the language model out of the box? And now we're going back to, what can we take from classical forecasting systems to improve it? And kind of what is that balance of having it be a pure black box versus incorporating some of these features? So in AutoGlow NTS, it has simple covariate regressors. In particular, we can use Cat Boost. It doesn't have some of those more advanced models that I was discussing of using in context learning to handle this, or the Kronos X. That's not been implemented yet. So we're going to use this simple covariate regressor flag. And what does the covariate regressor do? This is actually a tabular regression model. So in particular, we're going to be specifying it to be Cat Boost in this example. And we're going to fit it on the known covariates and static features to be able to predict the target column at each time step. And then the predictions of the covariate regressor are subtracted from the target column. And the univariate model then forecasts the residuals. So it's kind of a little trick to be able to forecast the residuals. So if we feed in this grocery data set, what do we see? We again see the time ID column. This is always required. The timestamp similarly is also always required. So here we see the frequency is actually at 1 week intervals. And then here we're going to have the features. So we're going to have promotion email. This is a binary feature of whether there's a promotion or not. And then we also have the unit sales is what we're going to be trying to predict. And also this promotion. So let's see if adding in the covariates helps. Was everyone able to load this data set? The other covariate is the scaled price. So we wanted to forecast the total sales. In this case, the prediction length is going to be 8 days. So first, to create our data set, we're going to, again, do the train test split. We can quickly run that. And we have 2 configurations of Kronos Bolt. We're going to do the 0-shot configuration without using the covariates. So that was our base model. And we're going to compare it to if we try to use this Cat Boost regression model as the covariate regressor. So how can we do that? The first line should seem familiar to everyone. We have the time series predictor. We're going to feed in our prediction length. We have to tell it what column now is the target time series. So we're telling that the target we want to present is actually the unit sales. And now we're going to give the column names of the covariate. So you could, let's say, input a CSV file that has more columns than this and just specify which ones you want to use as the covariates here. Now we're going to call the .fit method, feed in our training data, as well as the hyperparameters. So this is going to be the first baseline, which is Kronos 0-shot without covariates. So what we're running in the previous examples. We'll again use the Bolt small checkpoint, and we'll just name this 0-shot. And then we're going to be combining that with the covariate. So how do we specify this? You're going to have this additional line. Covariate regressor is cat. So this is the Cat Boost model. And then we're going to use the target scalar is still standard. And we'll name this the with regressor. I've again enabled ensemble to false, but I encourage playing around with setting this to true and seeing how the ensemble of different models also works. Okay, so here's where it's doing some of the statistics to see if you have GPU available. So on my laptop, it's just saying 2 CPUs, there's 0 GPUs available. So it will run on CPU. And here are corresponding arguments. Here it is able, again, to infer the frequency of weekly, and particularly with weeks starting on Monday. And this is, again, some of the data set statistics. So training data has 3,000 rows. And this data set actually has 319 time series with a median length of 23. Okay, so now it's trained both of the models. So training was 29.9 seconds. So we see this is our validation score of the small model. Again, it's the minus quantile loss, so we can rank them in order. And then here is with the regressor. So in this case, the smaller value is better. So we see the improvement of adding in the feature covariates. We have a smaller weighted quantile loss value. And then here's what you should see for the leaderboard. So we see that the Chronos with regressor is performing better than the zero-shot model. Any questions on this part? If not, I just have some facts at the end of the notebook, but everyone's already asked really great questions. So how accurate is Chronos? We've seen several examples of this. We found it to be effective in zero-shot forecasting, and we saw Chronos Bait often exceeds the statistical models and has comparable runtime to the TFT or patch TST. For recommended hardware, we saw that we can do simple fine-tuning and inference with smaller versions of Chronos and Chronos Bolt. But for our testing, if we want to use the larger models, we tested it on AWS on a G5 2x large or P3 2x large. So these are larger GPUs machines, but not as large as we did for the pre-training, which was on a P4 machine, 24x large. The Chronos Bolt, as we saw in the tutorial, can be used on CPU machines. It will just take a bit longer if you want to do extensive fine-tuning. And if you have any questions, feel free to email me or any other members of our team. All of the Chronos and AutoGluon is open source, so you can also create issues on the GitHub page. Great, so please let me know if you have any other questions. There's no multivariate support for Chronos currently in the open source. We have some of the deep learning multivariate models such as DeepVar, so that's using like a multivariate Gaussian distribution. Those are available in Gluon TS if you're interested in those cases. But yes, we're actively working on that. So hopefully soon we'll have like a multivariate foundation model. But yeah, there's been a lot of work on DeepVar and also Gaussian cupola models also on the multivariate side. Question? Uh-huh. Right. Yeah, exactly. So you get basically the softmax out, which will give you the probabilities, and then we're going to draw multiple samples from that distribution. So in typical forecasting, we're calling those the sample paths, for instance, and then that will give us the uncertainty estimate. Yeah, Bolt, it's different. Oh yeah, great question. So yeah, so the Bolt version is very different, and it's using more of the classical forecasting method. So it's similar to what's done in multi-quantile CNN or multi-quantile transformer. So there, the loss function is actually the quantile loss. So we're directly regressing on the quantile. So you directly output the quantiles that are desired. You don't have to output all of them. Let's say you're interested in the P90, you directly output them for the entire forecast horizon. So you don't have to do the expensive sampling procedure. Yeah, so that's based. Yeah, exactly. So the training is by using the quantile, substituting the cross entropy loss with the quantile loss function. Mhm. Yeah, exactly. So stock market is always more challenging because it's more unpredictable. So you'll see the accuracy pretty much drastically change. That's why we're looking at some of those problems with shocks, for instance, to kind of mimic, okay, let's say stock market or maybe a sudden surge in sales, right? Those are cases, and similar to the anomaly detection cases, where we can probably break some of the foundational models unless they've been trained particularly on those type of data sets. Be more challenging cases for them, at least, for sure. Question? You can run on multiple GPUs as well. Yeah. And that will typically be the fastest if you're running the larger model. We try to make it accessible with some of these smaller models to run on CPUs depending on your architecture. Definitely the pre-training that we do is multi-GPU. Question? Why we haven't trained larger? Yeah, so exactly. So we've looked at, as I mentioned kind of earlier, the neural scaling laws for language models. These actually don't hold here, similar to what we saw with the weather models. They do saturate after a certain model size. So it's not necessarily that the larger you go on these, the better. Is that a limitation? Probably on limited training data, possibly. We can probably push, by increasing the number of training data, push these models even larger and improve the performance. Because really, they shouldn't be saturating. We shouldn't kind of see this overfitting happen. But yeah, we didn't see significant improvement of going past the large model of the 7 to 10 million. That's what I think, yeah. We have an interesting project. We have Anon in the audience who's actually working on looking at the input of the training data right now. And particularly what we see, one difference between the time series data and language models, if you look at actually the input, is we see a low rank structure from the time series data versus for language model, even tabular models, they have a very high rank structure. Now, of course, that can be fixed as you propagate through the attention layers, the rank will increase. But at the beginning, even with the Chronos Bolt, even the wavelet tokenization, all of those kind of, since we're mapping one-dimensional time series to a higher dimensional space, have low rank embeddings. So we're looking at compression techniques that we can do there as well. But it's kind of an interesting difference in the time series data from also the language modeling. So it's how much is it limited data versus also kind of this low rank, inherent low rank property of it. Okay. Yes. Let me go back to the slides on that a bit. So we use a couple different methods. Most of the original Chronos was using Gaussian processes for the synthetic data. So if we go back here. Yeah, so the main idea is we take Gaussian processes with different kernels and we randomly sample a kernel from this so-called kernel bank. So you can have a linear kernel, RBF, periodic. The periodic is really important to input the different frequencies as well. And we sample those kernels and then we could actually multiply them together to get more diverse time series out. So we've been looking more into the synthetic generation on the tabular foundation model side, but it's kind of commonality with this. There's two features in the synthetic data to make it good pre-training data in a sense. So what do we mean by good? One is a diversity. So how diverse is the function class and how can we generate synthetic data to make it as diverse as possible? The second is its performance kind of on the target validation or test set. Is it a good performing classifier in the case of tabular data? But in general, you kind of want to increase the diversity of the space as much as you can by mixing these different functions together. So first, we experiment with Gaussian processes, and then in the Chronos Bolt, we also use recipe-based generation. So you could specify what kind of period you wanted, if you wanted to add linear, things like that. But yeah, there's actually a lot of interesting research to be done on synthetic data generation too. I think we could improve some of these initial results of the model purely trained on synthetic data not performing as well as real world data. Because we need some way to improve kind of the difference in the scale of the time series data to the language data since we have so much fewer. So I think a lot of active work on the synthetic data generation and also the in context learning side could be interesting. Question? How much of the data preparation and cleaning of the real? Yeah. So that's a good question. How much pre-processing of the pre-training data? Yeah. So it definitely depends on the data set and if it's already been cleaned or not. So a lot of the data sets you saw we used were from UC Irvine. We use the open source electricity traffic, which have been common benchmark data sets that we've used. So those didn't require too much, and also some of the ones used in the forecasting competitions. But when we looked at using Weatherbench, for instance, that required a lot more processing, especially because it was a spatial temporal data set that we were mapping to time. So some data sets required more than others. But our initial proof of concept worked surprisingly well, which surprised the team of how we got the base Chronos working, and we're still working on how we can improve that significantly. But yeah, I think at least doing the pre-training data, the most important was actually the diversity, and then just performing simple normalization was kind of the main processing step we took. Question? Mm-hmm. Yes. Right. Yeah, so that's a great question. I think similar to one of the questions we got earlier is on why do we want to actually discretize the time series into bins rather than passing in the raw numbers, let's say to a language model out of the box as a prompt. Yeah, that's a good point. Experimentally, we haven't seen kind of the prompt-based methods performing well if we just feed in kind of the raw time series values. So there must be some benefit actually to the first embedding layer. Potentially you could improve that by positional embeddings, things along those lines also. But yeah, I think that's a good point. It depends how much is it feasible too to feed in every time series value depending on how much data you have as well, where binning could be more efficient also. But I guess the idea is the original points have some type of continuous real valued notion. There's infinitely many of them, right? So we try to map them to like a discrete vocabulary to make it compatible with the language model at a high level. Mm-hmm. Oh, like the equilibrium or normal state? Mm-hmm. Yeah. Yeah, that's definitely an important thing to differentiate, right? Is it just repeating the seasonality or period, meaning it would be similar to like the seasonal naive method, or is it actually able to adjust? I think like this plot on the wave token is interesting for that. Let me pull that up quickly. Yeah, so this isn't exactly the scenario you're talking about, but let's say we do have some very high frequency and then going lower. So we do see that that breaks kind of the base model. And also, I think that gets back to some of like the shock data sets we've tested on in the pre-diff work, actually. That's how we kind of argue using diffusion models are better, any type of probabilistic model. We actually try to model extreme events there. So what's the extreme event by using the standard deviation of going +5 to standard deviations, let's say for extreme rainfall years, or -5 for extreme drought years. So we look at some extreme event prediction in that paper actually. But for Chronos, yeah, I think that would be an interesting use case. Also, if anyone has interesting kind of real world science data, feel free to email me your use case afterwards. We're really looking at trying to collect kind of real world weather or dynamical systems data to really stress test this more. And also larger scale. There's another use case during the break that I was hearing about of kind of larger scale water prediction with Chronos also. So feel free to reach out if you run it on your data. Don't be shy. Let's say if it's not working well, or if it's taking a long time to run, that's actually good news for us because that's more future work, and definitely look in to helping you get it run more efficiently. Great. Any other questions or any questions with running the tutorial? Yeah, I'll be around if anyone's shy and wants to ask me one-on-one questions or yeah. Sure. I'll walk around and see how everyone's